Now we are ready to go to the kinetics of your radioactive processes. Again, radionuclides are unstable and they decay to other nuclides by the processes that we just learned, like your alpha decay, beta particle emission, and so on. But do all radionuclides decay at the same rate? How many radioatoms or radionuclides remain after a given period of time? So after learning about the units of radioactivity, we are now ready to tackle the equations that can answer these questions. So let's define some variables. We have R sub T. This is the number of nuclei disintegrating per unit time at a specific point in time t. So we have the following equation. R sub t equals lambda times n sub t. Now, lambda is what we call the decay constant, and this is defined as the probability of decay per unit time for a single radioatom. And n sub t is the number or population of radioatoms present at the defined time t. Now, this R sub t can also actually be defined in terms of a differential. We have R sub t equals negative the change in the number of radioatoms over the change in time, or dNt over dt. Now again, we have the negative sign because we know that the amount or the number of radioatoms is decreasing. So in order to keep the R sub t a positive value, we introduce the negative sign. Now, if you've studied chemical kinetics, then this is just one of the equations that you have in chemical kinetics. In fact, this is a first order kinetics. All of your radioactive processes follow first order behavior. So using the equation that we just saw, let's try solving this problem. We have metastable technetium-99, okay, with a decay constant of 3.2 times 10 raised to negative 5 per second. How many radioatoms are there at time t? If at this specific point in time, the sample displays a radioactivity of 37 megabecquerels. Okay, so first, we need to recognize that we have a unit of radioactivity here, megabecquerel. And we will be using the equation that we just saw, which is R sub t equals lambda n sub t. So first, you must be able to recognize what megabecquerel means in terms of disintegrations per second. So at the given point in time, we do not know actually, but we are actually given all of the information that we need to solve this problem. So we have 37 megabecquerel, or this is 1 millicurie. And in terms of disintegrations per second, this is equal to 37 times 10 raised to 6 disintegrations per second. Okay. Now, the lambda is given for metastable technetium-99 as 3.2 times 10 raised to negative 5 per second. So we are asked for n sub t, or the number of radioatoms. And this is pretty easy because we just need to supply the information that we have. So you do the substitution of the values, and you should be able to get 1.15 times 10 raised to 12 radioatoms. So it means that any metastable technetium-99 sample displaying a radioactivity of 37 megabecquerels means that you have 1.15 times 10 raised to 12 radioatoms. So that's 1.15 times 10 raised to 12 radioatoms. Now, what about this problem? For the same radioactivity, how many radioatoms are there in a sample of iodine 131 with a decay constant of 10 raised to negative 6 seconds per second? Notice they have the same radioactivity or R sub T, right? And let's see how many radioatoms do we have in this sample of iodine 131. Will there be the same number of radioatoms? Well, you guessed, if you answered no, that is correct because iodine 131 has a different decay constant. So if you compute for n sub t, for the second problem, you will get 37 times 10 raised to 13 radioatoms of iodine 131. So the point here is that for the same amount of radioactivity, you will get a different amount or number of radioatoms as long as they have different decay constants. In these two examples, for 37 megabecquerels, there are approximately 32 times more radioatoms present in a sample of iodine 131 than in a sample of metastable technetium 99. Now, it is also important for us to calculate the mass or the amount of a radioactive sample because if we desire to administer a certain dosage to a patient, it is important for us to be able to compute for the correct amount in whether it's in terms of mass or volume. First, let us focus on calculating the mass of a radioactive sample. So again, in calculations like this, we make an assumption that the radioactive sample contains only the radionuclide under considerations and no other isotopes. So we are assuming that our source of radionuclide is pure. So for example, a 1 megabecquerel sample of a radionuclide of mass A will have this relationship. So you have N sub T, which is the amount or number of radionuclides, equals the rate or the radioactivity, which is given in disintegrations per second. So why is this 1 times 10 raised to 6? So please figure it out by yourself. The given is 1 megabecquerel. And we have the decay constant lambda, which has unit of per second. So if we are given A grams, okay, of this radionuclide, so remember, the mass number of this radionuclide is A, and we are given A grams. This means that we have 6 times 10 raised to 23 radioatoms, right? So the mass of one radioatom is given by this equation. You simply divide the mass number by the number of radioatoms, which is 6 times 10 raised to 23. Or if we have n sub t, or the number of radioatoms in a specific sample, then we simply multiply this mass of one radioatom by the number of radioatoms that we have, which is n sub t. Okay, now substituting this n sub t here, this expression for n sub t, so in place of n sub t in this equation, we replace it with this ratio. We get for the mass m of a certain radioactive sample, 1 times 10 raised to 6 times the mass number divided by 6 times 10 raised to 23 times the lambda. And the units that we will end up is grams per megabecquerel. Now we can simplify the constant values here. So divide 1 times 10 raised to 6 by 6 times 10 raised to 23, and we get 1.67 times 10 raised to negative 18 here. Or if we want the units to be in terms of the old unit Curie, then we can convert this 1 times 67 times 10 raised to negative 18 from megabecquerel to 1.67 times 10 raised to negative 17 in order for the unit to be millicurie. So, for example, what is the mass of a 1 megabecquerel sample of metastable technetium-99? So the mass number for this radionuclide is 99. And again, the decay constant is 3.2 times 10 raised to negative 5 second. So this is fairly straightforward because we are given the mass number and the lambda value. So what you do is you just plug in the values to our formula. So we have mass M equals 1.67 times 10 raised to negative 18 times the mass number divided by the decay constant, 3.2 times 10 raised to negative 5. And this will give you 5.17 times 10 raised to negative 12 grams. So since the activity or the radioactivity or the rate is 1 megabecquerel, then it's your choice whether to write there per megabecquerel or per gram. So per gram is actually quite it's simpler because we are given 1 megabecquerel sample. So it's 5.17 times 10 raised to negative 12 gram. Now, so we now know how to compute for the mass of a radioactive sample. Notice that the units of our that we get from our formula is gram per megabecquerel or gram per millicurie. If we get the inverse of this ratio, we actually get activity per amount, right? So if we inverse, for example, if we get the reciprocal of 5.7 times 10 raised to negative 12, the one that we calculated in the previous problem, then we will get a value whose units are megabecquerel per gram. So we are essentially getting radioactivity per amount. So this is what we call specific activity. So again, this is amount of radioactivity per unit mass of radionuclide of interest. And basically, this is just the reciprocal of the value from the formula that we just derived. The formula for the mass of a radioactive sample. Now again, all of our calculations are under the assumption that the radioactive sample is pure. So there are no other radionuclides or even stable nuclides present in our sample. Now we describe such sample as carrier-free sample. So there are no other stable isotopes or even long-lived radioisotopes of that radionuclide. So whenever you see a specific activity value, make sure to check if this specific activity is for a carrier-free sample. Most of the time, the values that you can see or the values that are available are that of a carrier-free sample. However, it is also possible to compute for the specific activity of a sample with the carrier. Just keep in mind that specific activities of samples with carriers are always less than that of a carrier-free sample. So again, it's because of the purity. Furthermore, when your radionuclide is part of a molecule, the specific activity can be generalized into the mass of the molecule rather than the element. So for example, in our previous problem, we are focusing on the metastable technetium-99. So it is possible for this radionuclide to be part of a molecule. And that molecule is pertechnetate with a chemical formula of that's TCO4 minus. Okay. So our metastable technetium is part of an oxyanion, pertechnetate. So instead of using the mass number of technetium alone, you can actually use the mass number of the whole molecule. So you need the mass number of the oxygen in this molecule and compute for the specific activity using that mass. So if our metastable technetium-99 is part of this pertechnetate molecule, so we can use the formula. So we have the formula for M, right? So we get the inverse of M, which is lambda over A times 1.67 times 10 raised to negative 18. So here, instead of 99, we substitute this with 163, which is the approximate molecular weight of pertechnetate. So the specific activity of a 1 megabecquerel sample of pertechnetate is given as 1.18 times 10 raised to 11 millibecquerel per gram, or 3.4 times 10 raised to 9 millicurie per gram. So you see, it's in terms of computing for the required amount given a certain radioactivity, it's easier to work with specific activity. That is why in nuclear medicine, knowing the specific activity is very important. Now let's go to the law of decay, or the exponential law of decay. So we saw two equations containing R sub t. So R sub t again is defined as the number of disintegrations per unit time, or disintegrations per second. So this is basically what we call activity, right? Or radioactivity. So we saw R sub t being equal to negative dn sub t over dt and lambda times nt. So it is possible to equate these two. So we have this expression, and you work out by integrating the equation, and we get this relationship. So we have n sub t, which is the number of radionuclides at a specific time, n sub 0, which is your starting or initial amount of radionuclides, times this exponential term, so e raised to negative lambda times t. So if we want to look at the behavior of our nuclear reaction, we can plot time on the x-axis and n sub t on the y-axis. And you will observe that you will get this exponential graph. Okay, so it is decreasing as time goes by. Obviously, your amount decreases, right, as your radionuclide undergoes radioactivity or nuclear reaction. Obviously, the amount of active radionuclide will decrease. And the decrease is exponential in behavior. Now, if we try to plot the same values of your n sub t and time on a semi-logarithmic paper or semi-logarithmic scale, then we will observe a straight line. In fact, it is also, it can also be, this equation can also be transformed into a linear form just by getting the natural logarithm of both sides of the equation. So we will get this form of the equation. And if you plot time on the x-axis and ln, or natural logarithm of n sub t, on the y-axis, you will get a straight line with a negative slope. So this is your normal coordinate axis. This is not a semi-logarithmic scale. And your decay constant or lambda is equal to the slope of this decreasing line. Okay, the slope is equal to negative lambda. And since the value of the slope will be negative, the negative signs cancel out and you will get a positive lambda. So always remember your lambda values are positive because they define probability. So you don't have negative probability values. Furthermore, just by looking at this equation, you can also determine the value of your initial amount of radionuclide. So you have your y-intercept here. Your y-intercept is equal to the natural logarithm of the starting or initial amount of radionuclides.